Hello, everyone, and welcome to another great day of chemistry. So today we're going to be looking at isobaric conditions, which means we finally get to talk about our good old friend enthalpy. So far we've mostly been looking at internal energy. And so internal energy is going to really focus under heat transfer under isochoric conditions. The problem is that in reality, we often don't work under constant volume conditions. So if we want to try and look at non-constant volume conditions, we can rearrange our solution for heat as taking that first law and now solving for the heat is just going to be the changes in internal energy minus work. So this is going to be a robust way of looking at the changes in heat. So we can get that internal energy change from our CV delta T, and then our work term from our good old friend PV. Now, notice that under isobaric conditions, we get really lucky because that work term goes from negative PV to negative P delta V. Though notice I did drop that technically that is going to refer to the external pressure, not the system pressure. Now, this generates a fairly nice equation for isobaric heat. So the isobaric heat is just going to be the change in internal energy, which again comes from CV delta T, plus that constant pressure times that change in volume. Again, note, technically, this is going to refer to constant external pressure, not constant system pressure, and that can cause some issues. But we now have a nice constraint definition for a constrained heat equation. And notice whenever, just like when we looked at isochoric conditions, when we constrain our heat, we now suddenly go from a heat being a path function to a state function. So we can assign this a new state variable. So this new state variable is going for the isobaric heat is just simply known as the change in enthalpy. So you can get the change in enthalpy as the change in internal energy plus P delta V. Note, though, this relationship only holds under isobaric conditions. So it would be nice if we could generate a more general description that allows for how I can relate enthalpy and internal energy when pressure is allowed to change. Now, one of the ways we can do this is simply just by moving that change from only applying to the volume to applying to both the P and the V. So the robust description is change in enthalpy is going to be equal to change in internal energy plus the change in PV together. Now, there's a useful bit of calculus we can do when I have change of a two-property system. I can calculate this by holding one variable constant and then holding the other variable constant. So we can get the change in internal energy is the change in internal energy plus that P delta V that we had before. So this is all the same, but now we add on this extra term, volume times change in pressure. But note under isochoric conditions, this last term will fall out. So we still get that desired expression that we had earlier. So notice this allows for the conversion in between enthalpy and internal energy under any conditions, whether they're isobaric, baric, or isochoric. Now we can go ahead and put this into an infinitesimal basis where we take this for this second equation, but instead of the delta, we just simply turn it into d. This way we can use all of our classic calculus tricks. So the change in enthalpy is equal to the change in internal energy plus the change in pressure and volume together. And again, if we split this apart, we still get dH equals du plus pdv and vdp. So again, these are going to be our good relationships in between changes in enthalpy and internal energy. Now, sometimes we usually focus on changes in internal energy and enthalpy, but for mathematical reasons, it's good to also have this in a absolute term. And we can actually get the derivation of enthalpy with respect to internal energy simply by just adding in this PV. One of the ways you can think about this is if I integrate the previous term, I get rid of the d's on every single term, and I get this nice general expression, which again, still, if I take the derivative, reproduces the same relationship in between our three properties: changes in enthalpy, internal energy, volume, and pressure. Now, using this expression, we can actually get a little bit more clever description of enthalpy by saying, hey, the change in internal energy is going to just be the same as the change in heat plus work using the first law of thermodynamics. So the second term is exactly the same. Well, we also have some good descriptions of work. So work is just negative PdV under a very robust description. Well, wait a minute. We now have two equations for PdV, and they should end up canceling out. So this gets us a nice description that the change in enthalpy is just simply going to be the heat plus this volume pressure term. And this will generally hold. And that's very nice. But one of the things that we'll often so in this case, note that this enthalpy is going to have a pressure dependency, but it'll also have a temperature dependency, because again, the change in heat is going to be typically measured by changes in temperature of the system. So the enthalpy has both a pressure and a temperature dependence. And we can go ahead and really compare enthalpy and internal energy by looking at these temperature dependencies. So let's go ahead and do kind of a robust comparison in between these two terms. So again, note internal energy is going to be related to the heat minus VDP, and enthalpy is going to be related to the heat plus VDP. So again, note that internal energy is going to have a volume dependence and enthalpy is going to have a pressure dependence, but both will be related to the heat. So in both cases, we can get a good description of the heat by constraining these systems. So that way we make sure that I'm in the internal energy, I don't have to worry about the volume term, and then the enthalpy, I don't have to worry about the pressure term. So it turns out the change in internal energy, as we saw before, is going to be equal to the constant volume heat transfer, because again, that second term drops out. So thus, it's going to be related to CV delta T. But note, change in temperature and internal energy are both state functions, so this will always be true. And we can do the same thing for enthalpy under constant pressure conditions, because under constant pressure, any transfer of heat is going straight into the enthalpy. So we'll note that this really shows that I can't relate heat directly to the changes in temperature because it will always have a different heat capacity. But that heat becomes a state function if I constrain the volume and pressure. Under constant volume, the heat's going to be the same as internal energy. Under constant pressure, it's the same as enthalpy. But this, by definition, means that these two heat capacities, CV and CP, will not be the same. So this CP is going to be our isobaric, or constant pressure heat capacity. And it's going to include usually a little bit more energy, because it turns out as I heat the system, usually we also have a change in pressure. Uh, oh, uh, if I heat the system and the pressure is held constant, that means I'm going to have a change in volume as the system expands, meaning the system's going to do some PV work. So next time, we're really going to be looking at these two heat capacities and comparing them back and forth as we really define isochoric versus isobaric heat capacities. Until then, take care.